Hi, welcome to QCI's first webinar. My name is Richard Nelson. I'm the Senior Vice President of Business Development for QCI. Today's topic is Beyond QUBOs, Efficient Quantum Optimization. We'll be discussing our accessible quantum optimization machines for non-convex and combinatorial problems. It's my pleasure to present Dr. Laknian and Dr. Ali Miri today to present their findings from their recently published paper, Entropy Computing, a Paradigm for Optimization in an Open Quantum System. There's a link to this paper and several ways to get in touch with us at the end of this presentation. Note, we also have a live Q&A box for you to submit questions during this presentation. By the way, the image to the right is not a, you would go back. Excellent. There you go. By the way, the image to the right is not one QCI quantum computer. It's actually a stack of 8 of our Dirac 3 systems in a standard server rack. All right, now we go. Just a little bit about QCI. Our 46 employees are developing photonic hardware solutions that are setting new standards for high-performance computing, cybersecurity, imaging, and sensing applications. There's a QR code if you'd like to explore our full line of technologies and products. QCI has in-house expertise to control our own destiny and develop the products that will be most impactful for our customers. If your solution requires quantum physics or integrating optics, hardware, software, mechanical engineering, or product design, it can all be handled directly by QCI. As you can see from the timeline, QCI is not new to the quantum computing space. We have a deep experience in the entropy computing approach with open quantum systems. One of our near-term goals is to create a gate-based quantum computer very soon. Today, we offer an analog-based quantum optimization machines like Dirac 3, which produce the excellent results you'll see today. Expanding on our in-house capabilities, I'd like to give you a quick update on our thin film lithium niobate Foundry. It's the first of its kind fab in Tempe, Arizona, and will produce photonic chips as seen near Abraham Lincoln's beard on the penny. It's a very exciting new chapter for QCI that unlocks the roadmap to scale our technology into more markets that require quantum hardware and photonics with reasonable size, weight, power, cost, and cooling specifications, aka SWaP C2. Speaking of SWaP C2, this is our Dirac 3, an entropy quantum optimization machine. That's not a component, that's the entire system. It can handle integer and continuous variable optimization problems of up to 954 variables. It operates at room temperature in a standard server rack and uses the same power as a medium-sized laptop, all at a reasonable price point. Putting it on your premises guarantees data security and privacy and eliminates latency and queuing. All the work in the presentation was done on the Dirac 3 or its binary predecessor, Dirac 1. Let's talk about some real use cases done on QCI quantum computing hardware. These were done on the Dirac 1 system. As part of the BMW challenge, we optimized placement of sensors to maximize coverage for autonomous vehicle guidance. There are 1,350 possible sensor placement options and 500 critical points to cover using 3,854 qubits. With Rabobank, we trained a fraud detection model containing 144,000 records and 587 features. But like the real world, only 0.1% of the transactions in the dataset were fraud. We used QCI's Boost model, and it performed comparable to current state-of-the-art classical models on the very first run. In partnership with VIPC, we are looking at helping autonomous aerial vehicles minimize their flight risk, both to itself and to the public on the ground below, and still complete the journey within the time and battery life requirements. One little housekeeping item, you may have noticed the blue bar summaries on the left side of the slides. If the presentation goes into some technical detail outside of your field of study, the summary in the blue bar should help keep you on track. Our agenda for today is to present our entropy quantum optimization machines, their advantages, their current performance, and then follow up with a Q&A discussion, including a peek at our capabilities roadmap and its implications for quantum and photonic hardware moving from static infrastructure to edge devices. Don't forget to submit your questions to the Q&A box at any time during the presentation. With that, I'll turn the presentation over to Ali Miri.
Thank you, Richard. Hard optimization problems refer to large classes of optimization problems that have computational complexity, grow rapidly with the size of the problem. Perhaps many of you have heard of the traveling salesman problem, in which a traveler is supposed to go over a number of cities with given distances and return to the original location with some constraints that you don't want to pass a city more than once, and then and you want to go over all the cities. There is no known polynomial time algorithm for solving this problem. And the search space grows factorially with the number of the cities, depending on how you want to count it. If you want to count all the cities as a starting point, the possibilities are actually with n factorial. So if you have 6 cities, for example, the possible routes, they're going to be 720. But if you go to 10, then it quickly grows to 3.5 million routes. So imagine if you go to slightly increasing to 20 cities, then tracing the number of routes become basically intractable. And this is a general trend in the case of NP-hard problems, that there are no known algorithms with polynomial scaling of the computational complexity with the size of the problem. They could be exponentially general. So, just making sure on the next slide. Because of these problems, and we'll discuss briefly and how important those are in various real-world problems, because of this, there's a lot of effort for coming up with new hardware to tackle such problems. In the physics community, there is a particular interest in solving the Ising problem. This is inspired by the Ising model that involves a Hamiltonian over discrete binary spins. And there is the terminology of QUBO, quadratic unconstrained binary optimization. That's also in a way mappable to the Ising. And there's great interest again in the physics community in solving this problem. Here I'm listing some of most notable efforts on the quantum end. We have the gate-based quantum computing by utilizing algorithms like the quantum approximate optimization algorithm can be used to solve the Ising problem. We have the quantum annealers that are designed specifically to solve combinatorial, to solve optimization problems, including combinatorials, of course. And on the classical end, we have the somewhat recent notion of the coherent Ising machine. It is a classical solver that utilizes collective behavior of OPOs, optical parametric oscillators, to solve the Ising problem. There are digital annealers that are designed for efficient simulation of the dynamical differential equations governing Ising machines, for example, or other types of oscillator networks or dynamical systems. On the other hand, here we would like to dig into our recent notion of entropy computing. It is an alternative approach, and it offers great flexibility to go beyond the Ising. So, and why that is important to us is because of a range of problems that go beyond Ising. Consider a large number of real-world problems that are NP-hard, like, for example, the protein folding, graph partitioning with its numerous application in social network, fraud detection, etc. Traveling salesman problem and its many families that are central to logistics. Graph coloring that is directly relevant to scheduling problems. Portfolio optimization, and circuit routing. In terms of the nature of the variables involved in this and in other NP-hard problems, can in general categorize them in continuous, discrete, and a mixture of these mixed integer problems. A lot of this can be mapped to an Ising or QUBO problem, which is the core of the hardware that I presented in the previous slide. But that often comes at a cost. Either we have to use some approximations, or we need to bring additional variable to represent non-binary variables with binaries, or to get rid of non-quadratic terms, which is the only thing that an Ising or QUBO solver can handle. Again, we need to use approximation or come up basically with techniques, and in particular, adding additional variables. That's what we call it, a quadratization. In the physics community, again, spin models are popular models for emulating optimization problems. And beyond the Ising, we have generalized models like the POTS, it's a discrete model, and XY and its generalizations like Heisenberg and N vector that they cannot be represented with an Ising or QUBO. And we'll discuss that these can be simulated with Entropy Computing, and particularly with Dirac-3. That is the main focus of this talk. So let's consider a simple example. A discrete 5-level variable, let's call it x, and let's say the objective function that we want to tackle is the simple form of 87 times x, and x again is between 0, 1, 2, 3, and 4. To represent a cost function like 87 times x, this 5-level variables should be represented with 5 2-level variables. So it takes 5 variables to represent that. And in addition, you also need to incorporate large coefficients for these binaries, which can hit the limit of the hardware range of the dynamic range of the variables in the hardware. So QCI currently has 2 optimization solvers, Dirac-3, Dirac-1 and Dirac-3. These are available for external user, as we'll discuss soon near the end of this talk. Dirac-1 is an Ising or QUBO solver. More specifically, it handles problems with an objective function that are described at the bottom left of this panel. They involve linear and quadratic terms in binary variables. And then we have Dirac-3, that is, on the other hand, much more flexible in terms of the spin models. We can show that it can handle POTS K and N vector, and as well as other complicated models of linear and nonlinear. But it can be even more general if we just look at the mathematical form of this objective function described at the bottom right. That it, as you can see, it involves linear, quadratic, cubic, quartic, and even higher order polynomials over variables that can be continuous or integer or a mixture of these two. This is part of the encoding that we'll discuss soon. So before I go to Dirac-3, let's talk briefly about our binary solver, Dirac-1. We are showing the results to a benchmark max-cut problem. Here the goal is to partition a graph into 2 groups such that the number of the edges between the 2 groups is maximal. Or if it's starting with a weighted graph, we want to have the maximum sum of the graph edges, a weight of the graph edges that are between these 2 groups. Our results indicate that we managed to find a ground state or very high quality solutions when the time to converge to such solution is scaled only quadratically with the number of the graph nodes. In this example, we show the result for the particular graph with 100 nodes, what you can see on the top right. This is taken from the Big Mac library. It's a library of benchmark max-cut problems, and the ground state is known to be associated with a cut size of 1434. We see that with the highest probability, Dirac-1 is finding the ground state, and other solutions are in a small range deviating from the ground state. And we showed that by scaling the problem, as you can see at the bottom right panel, with highest frequency, we find the ground state in case of graphs that were known from that library that I mentioned. And in case of larger graphs that we were not aware of benchmark problems, we randomly generated graphs with similar probability distribution of those taken from the Big Mac library and find that our results are actually very close to a theoretical upper bound from the literature. It's important to note that that's an upper bound. So let's go back to Dirac-3, which is the subject of this talk. Coming back to Dirac-3, let us dig into the hardware in the next 2-3 slides. Dirac-3 is built on the concept of entropy computing. And starting from a given optimization problems, like the one you see visualized with that 5-node graph on the left, the target Hamiltonian is mapped onto an effective dissipative operator that hosts the propagation of photon qubit states to solve an optimization problem in the photon number Hilbert space. And this approach induces loss or decoherence into the system to suppress the evolution of unwanted states while promoting the evolution of qubits that represent lower energy states of the corresponding Hamiltonian. So the key elements are that this is a photonic system. We use time bins to represent photon qubits, and the variables are encoded in the photon number Hilbert space of those time bins. And more importantly, we have an open system that involves loss and decoherence in our favor. Mathematically, we can consider the system in a mixture state described by the density operator, like what you see at the bottom, at time equal to 0, when Pn is the probability of different states. The evolution in the Markovian limit can be described with a propagator like what the last equation, the middle. And as you can see, because of the imaginary factor that comes because of loss, the states with higher energy in general, they will decay faster. And this way, basically, we can promote the ground state through an amplification process. So let's see an all optical physical realization of the system. Here you can see the implementation of the concept of entropy computing. In here we have an optical feedback loop in which the qubit states, again encoded in our train of time bins, are circulated until the initial mixture state approaches the desired state, which is the ground state or high quality solution of the target Hamiltonian. We can decompose roughly the system in 3 main pieces. There's the entropy coupling and amplification, quantum fluctuation from spontaneous emission, and optical amplifier are used. We have the photon mode mixer encoder to create the initial state and to embed the desired Hamiltonian, which could be through a network of MZIs, Mach-Zehnder interferometers, and delay lines. Again, it can be done all optically. It can be done programmable fashion. And the mode projection that involves a loss medium to implement both linear and nonlinear loss mechanisms. And this can be done through the so-called quantum xenoblockade. It's an effect that can occur in the regime where the loss is stronger than the coupling of the fiber loop or the waveguide to the cavity, and becomes nonlinear as the state populating the cavity will effectively prevent additional photons entering the resonator. So let's look at the current physical realization of the concept of entropy computing. And this is indeed the current hardware underlying Dirac-free. While all photonic realization is the next generation of Dirac machines, Dirac-free is a hybrid system at the moment that utilizes photonics in conjunction with electronics to close the evolution loop in a so-called measurement and feedback system. Here, the red and green path, as you can see, are showing the optical and electronic sections of the system, while the photon qubit states evolve in the fiber loop. They will be detected through a photon detector and be converted and converting basically the time bins to digital, and then utilizing an FPGA to create the interaction terms, and then utilizing a digital to analog converter signal to create a signal that will be utilized to generate create the photon qubit state using an electro-optical modulator for the next iteration in the loop. And let's briefly talk about the qubit states as well. As we said, we consider time bins to represent different variables, and a single photon wave function promotes quantum superposition among all time bins. This is how the encoding is done. And in the decoding phase, on the other hand, by using a photodetector, the wave function collapses into one of the time bins, which will be stored as a histogram This histogram will eventually describe the state of the system. This is a brief description of the hardware. Let me pass this to Lag to talk about the advantages of graph.
Thank you, Ali, for giving a really great insight of our direct system. So next, I will discuss the advantage of our implementation. Most of these material you can find in our paper, but some of them are under preparation. So as we know, creating a technology not only work in the lab, but also in real life. We consider both the speed, the quality, and also sustainability and scale. So the first advantage that I would like to share is the flexible in encoding. So our objective function here, the Hamiltonian, involve a polynomial up to fifth order and variable vi or spread over a discrete space, and which is beyond the binary space. So first, when we're looking at the continuous encoding, the quantum state are encoded into Hamiltonian. The quantum state are encoded into 10-bin qubit over a train of 10-bin and create the single photon wave function. The linear loss is mapped directly into the wave function and perform single photon counting at the measurement side. After many measurements accumulate photon over time, that information is processed, feedback through electronically to provide the next modulation signal of the single photon wave function. So after some time, a single photon count can be observed that the probability amplitude no longer changed, and that is mapped directly back into the vectors, the state vector, which are normalization factor, of course, which is equivalent to the sum of the resource, which is the sum of all the variables. So that's how we do that in the continuous variable. In terms of integer, similar single photon wave function is created, but now the mapping is not is on the position of the 10-bin. So to artificially emulate the energy level of an atom, let's say if we want to create like a 5 level, then dedicate 5 10-bin slots to present level 0, 1, 2, 3, 4, and so on, similar for qubit, qubit. So with go through similar feedback loop, after many feedback loop, collect single photon counting, accumulate, and the bin that with the highest photon count will be considered as where the energy, where the level collapse into. And that map directly back into the integer level. So with such convenient encoding method, we can start combining different type of variables. So for example, if a long fiber loop, we can divide it in 3 different sections, let's say X, Y, Z, and dedicate some of them for binary, some of them for integer, and some of them for continuous, all in one. So that means the objective function with mixed integer can be mapped directly into the system. So this advantage promise to promote the increase in precision, solution quality, and at the same time consume much less resources by eliminate the need for auxiliary variable to map to. The second advantage that we basically the original motivation of creating direct system is the high order of interaction. So the objective function here go up to fifth order. So there's multiple way of implementing it. One of the method is we can use spatial domain where each variable is implemented into a binary phase of a pixel on a, for example, like a spatial light modulator, and the Gaussian beam light, when it's focused through some Fourier lens, pass through a nonlinear crystal, and that promoting the second order of the electric field. And when being measured in intensity, that give combined with the nonlinear effect, for example, like second harmonic, then that promote full body interaction. That is in the spatial domain. In the temporal domain, one can couple a small portion of light and pass through a system of optical switches and delay line, which basically create a Mach-Zehnder mesh and multi-port, and combine at the end and couple back into the feedback loop. So that implementation will promote all-to-all connectivity and multi-body interaction. So both of these approach, why we are actively progressing, it is difficult to add in to keep the system stable and with a good scale. So the current approach, we use a measurement feedback base where the quantum state pass through a nonlinear circuit detected by single photon detector, and that information is measured and apply matrix multiplication over FPGA, and using digital to analog converter to recreate another single photon wave function back into the optical loop. So with such capability, we allow Direct3 can take in directly a multi-body interaction, which provide the advantage of skipping the embedded step, which basically like a quadratization reduction, and that step sometimes change your search space or require the need for auxiliary variables. And later on, Ali can show some of the interesting results we found with this direct mapping. Another advantage is the solution quality. So here we perform a study on a non-convex energy landscape. So you can see that we have 3 different local minima and 1 global in the corner. This is a 4th order non-convex problem. So we compare classical gradient descent and Direct3 with different initial condition to see how the evolution look like. And interestingly, the dashed line is gradient descent, and the black solid line is Direct3. And we observe a quantum tunneling-like behavior where gradient descent fall into the nearest local minima, and Direct3 constantly jump and ignore all the local one and start to approach to the global minima at the corner. So this clearly shows that the fact that the quantum fluctuation inject every feedback loop has enabled larger search space. In terms of speed, the speed coming from both combined optical and quantum. And what that means is, let's say in our hybrid implementation, the speed coming from very convenient large optical bandwidth of encoding, also the fast speed of single photon detector with low dead time. And when observing a non-convex problem compared between Direct3 and classical gradient descent, we can see that with the same number of sample, Direct3 return the solution much more often due to the quantum fluctuation, and that is the overall give us a faster speed thanks to the quantum fluctuation. In terms of the optical feedback implementation, of course, beside the speed of light and the large optical bandwidth, just like the hybrid system, the speed also comes from the most competition advantage in laser mechanism. And the quantum noise enhance the solution quality come from spontaneous emission in the amplifier, optical amplifier. And because of that, we have run many NP-hard problems and observe polynomial TAM compared to when the number of variable increase. That is something we're very excited about compared to annealer superconducting base, which is follow an exponential scale, which already such a huge improvement compared to classical, which is completely unpredictable. And the last advantage that people often overlook that we're really excited about is the energy efficiency. So as we know that we have larger data need to be processed, high performance computing become even more necessary, and data centers are being built every day. Back in 2010, power consumption by data center only 1%, but it's reaching 13% by the end of the decade. But when looking at the distribution of how does the power consumption look like, half of them going to running the server on computing, and the other half is on just cooling. So if we can eliminate the cooling and computing with lower power consumption, then that is an incredible sustainable solution when moving to photonics. So here we took a small data set using Direct3 solving a supply chain NP-hard problem. We run with different number of variable from 10 up to almost 900, and constantly measure the power consumption over 3,000 seconds. And it's pretty much fluctuate around 24 watt plus minus 1.5 watt-ish. And so combined with the auxiliary electronic, which is fan or temperature controller, those actually consume more than the system itself. So total Direct3 consume about like 100 watts. And this is just the beginning, so we're very excited about this number. And just briefly compare in like supercomputer is in the range of megawatts, or annealer superconducting base in the range of kilowatt, which is already a huge improvement. But the cooling system is most of the power goes to the cooling system. Or coherent Ising machine, most of the power going to pumping the laser, but still already an improvement. So overall, we already bring it down 100,000 times more or less compared to supercomputer. So with this, not only we reduce the carbon footprint, but this allow lower operational cost. And such low power demand from Direct3, it can be easily integrated with other system like put it on a plane, put it on a boat or a drone, and become an edge device. And with that, I'm gonna get it back to Ali to share some excited result, current performance of Direct3.
Thank you, Jack. Let's go over a few examples that we benchmark Direct3 with. Let's start with a continuous variable example. As we said, Direct3 can handle continuous variables in its general form and in the objective functions that you can see above that involves polynomial terms with coefficients that in general that can be as dense as possible. The only restriction is that the J, T, and Q tensors, they should be symmetric. We consider QPLib 18. It's a quadratic problem from QPLib library. This is a library of hard quadratic problems. The problem is described mathematically with linear and quadratic terms. It is non-convex. It contains 50 real valued non-negative variables, and it has a dense matrix of coefficients. We ran this problem with drag-free and found with more than 80% probability the ground state. And what you can see in red is the histogram of results over multiple runs that are compared with a conventional gradient descent algorithm, and which is shown with blue. And as you can see, basically, in many cases with the gradient descent, we are trapped into the local minima. We observe that the system converges to its final state in a few hundred iterations, as you can see in the panel below that shows the evolution of the state with the number of iterations. And the convergence is very good after a few hundred, basically, iterations. And this, we see that a general trend, somewhat irrespective of the size of the problem, we see this trend. And we did an interesting study and explored the result versus the mean photon number, which is an important parameter in the system. Roughly speaking, we can say that for lower mean photon number, we are moving toward the quantum regime, and vice versa. We can move to the classical regime for higher mean photon number. We observe that with higher likelihood, we find the ground state when moving toward the quantum regime, while the noise is becoming problematic in very low mean photon numbers. So there is a sweet spot to consider for achieving best results. And of course, note that as we expected, basically, the time to converge increases when we go for lower mean photon numbers, and this is something that we expect from the experiment. Let's move on to a discrete optimization problem. We start with the POTS model. The POTS is a generalization. POTS model is a generalization of the Ising model, but two-state spins are replaced with k-state spins in general. In the multi-state POTS, and again, I'm emphasize that this is the standard POTS model for the reasons that I will explain soon. This multi-state spins allow for direct representation of many combinatorial problems, such as graph partitioning, graph coloring, image segmentation, VLSI design, and such. And we can see that basically we can handle this readily with Dirac theory. The Hamiltonian is shown basically on the top left, as you can see, with delta functions. One technique that we use in the encoding is to represent one spin degree of freedom as a classical superposition of three orthogonal vectors, which can be three variables in the or three of our time bins in Dirac theory. Mathematically, we have that superposition, and we can put a norm one regularization that the sum of the magnitude basically of those three levels should be 1. And then we can write the Hamiltonian in this form, as you can see, that is dot product of basically two spins plus the norm one regularization. So how we encode the spin in Dirac theory, we can consider three of the time bins for one spin, and then we can basically take these chunks of the spin, three variables, and repeat that. And that can be done both at the hardware level, or it can be done in the programming level. And we have tried both of them. And considering, for example, a graph with 30 nodes that I'm showing in the bottom left panel, I can take the adjacency matrix of that, and according to this encoding that I did, I embed that in a higher dimensional matrix. And once I run the problem, I see that the final state for each one of the variables for spins is this in this three-dimensional space. The interesting fact is that all of these spins are along the axis, the three orthogonal axis. So it's a very simple post-processing to distinguish basically these spin degrees of freedom. So let's consider an example that we ran through our standard POTS model. We consider POTS 2, or basically Ising, POTS 3, and POTS 4 solved in the same graph. we can equivalently say that this is solving the max 2 cut, max 3 cut, and max 4 cut, which means that if you start with a given graph, we want to partition them into 2, 3, or 4 partitions, such that, again, we have the largest cut size basically, and we draw a line in between. So what I'm showing is the results from Dirac-3 in 2 relaxation schedules in red and green, and at the bottom I have the results from SDP. We observe that in all cases, Dirac-3 is finding better results with higher probability. The ground state is found compared to the SDP, and SDP is short for semi-definite programming. It is well known that that can guarantee 87% success for a max cut problem, an approximate method. And later on, of course, this is our earlier result. We tested this with simulated annealing, and still we observed that Dirac-3 is outperforming. And one interesting fact is that, especially when we go to higher order partitioning, or going to parts 3, 4, and so on, see that the performance of the gap between the performance of Dirac-3 and SDP is actually increasing in that regime, which is a very interesting observation. Let's move on. We have considered the generalization of Ising to spins having multi-states, which was pots. And then we can have the generalization in a different aspect, and that's when going from a graph to a hypergraph. Conventional graph has pairwise interaction between nodes, and that's a visualization of some Ising problem, for example, because it has quadratic terms with exchange terms that can each be represented with a graph edge. Consider now that you have a hypergraph that has interaction that has basically on top of regular edges, it has hyper edges, triplet of edges, and even higher order in general. Consider the example that I'm showing at the bottom, a random graph that the edges are shown with lines, and then I'm plotting basically with triangles, free edges or hyper edges that involves 3 nodes that are shown with triangles. You can see by slightly increasing the probability of having those hyper edges, the graph quickly is becoming filled on and just visualizes the complexity of this problem. And again, equivalently, this is as if we are solving the Ising problem, for example. If you want to solve an Ising or a Potts problem when considering higher order interaction terms like cubic, quartic, and so on. So we consider the cubic at this point, and we consider a graph that has 3 edges or hyper edges that involve triplets of nodes. And then we solve the Ising parts 3, 4, and 5, and this on this hypergraph. Again, equivalently, we can call it max cut, 3 cut, 4 cut, and 5 cut. And with Dirac-3, with a regularization parameter that is shown in here, which is not even optimized, we observe that in general, we are getting with much higher probability the ground state for each one of the 4 models with Dirac-3 compared to simulated annealing, which is a very rigorous heuristic method with giving it a lot of time basically to converge. And in the case of max cut or Ising, we observe that the average solution for simulated annealing is slightly better, but even the average becomes much better in case of Dirac-3, especially again when we go to higher order interaction, when we go to higher order cuts, basically. It's a general trend that we observe. Let me hand this back to Black to describe the real-world examples of these models.
Thank you, Ali. So the last thing is we provide sharing a current use case. We helping NASA to denoise the sunlight in satellite LiDAR images. The sunlight has a well-defined noise profile. that happen to obey the Poisson statistic, which is similar to the fluctuation that we observe on direct 3. And it's well defined, so we know the mean numbers, which is basically you can figure out the variance, and it's uniformly distributed over time. Meanwhile, the ground truth, the image that you want to capture, are highly coherent spatially and temporally. So turning this denoising problem into an optimization problem, which basically find the noise profile that minimize the variance difference between the noise-free profile, like variance of Si minus Ni, which is the signal and noise, and the variance of signal minus the variance of noise. This is one of the method. And using direct 3 to solve this optimization problem, we observed some interesting initial results. Look at on the top is the original image, the real image from the satellite. When mixed with 20 times noise, I mean, with eye, you still kind of see a little bit of it. And the bottom, we retrieve the image pretty well. Then go ahead, apply 200 times noise. Then the signal and noise are almost embedded with each other and cannot really observe much. But on the retrieving image, most of the main feature has been recovered using this method. Basically, we use our entropy quantum optimization machines to simulate the background noise, turning this into an optimization problem. And this is an ongoing project, and look forward to show even more advantage when we go to higher order.
That's great. Thank you very much. Thank you, Ellie. That was wonderful. So while the moderators are kind of reviewing the submitted questions, I thank all the audience members that submitted them. We have a few more than we were even expecting, so that's great. So we're going to sort through those and pick a few to talk about in front of the group. While we're doing that, I wanted to take a couple of minutes to show you where QCI is headed and how we see our capabilities developing to meet our customers' needs. So basically, as we continue to innovate through this, through increased variable count, smaller size, decreased energy consumption, our devices will put very sophisticated computing power into edge devices. As the variables increase by each order of magnitude, I'm not sure that this slide properly captures what exactly we're giving to our customers. So this slide does a little bit better job at it, I think. So it shows that compared to a CMOS type system, integrated photonic platforms are superior to electrons for speed, energy consumption, security, signal integrity, and cooling. As photonic hardware makes up a larger percentage of devices, the size, weight, power, cost, and cooling benefits will impact entire industries significantly. Computing power is increasing at a logarithmic scale, and power consumption has only modest increases and then decreases dramatically when you add the photonic hardware that requires very little power to operate and runs much cooler than a traditional CMOS system. So now I'll leave this slide up for a little bit. If you want to, you can grab the QR code. You can also see there's 3 ways to contact us as well. Through support, just general questions and things like that. I just put attention Lack or attention Ali or myself on that. And then if you have a sales inquiry, there's an email there, and there's also for some of the investors on the call as well to do that. There's also a link to the paper. You can get as much detail as you wish on that, and it talks a little bit more about entropy quantum computing in general. And then if you want to see our website, there's also quantumcomputinginc.com. And there's a QR code there as well, obviously.
So we already read questions to the Q&A.
All right. So I'll put the slide up and At the Q&A session there.
Let's do one first.
And where do I find that?
The Q&A button at the bottom.
Q&A button at the bottom.
I
Thank
think we
you.
should answer this one from.
Oops,
I'll put it in the.
hold on. I'm working on it. There we go. I got it. Sorry about that.
Let's do the third one down from Nishikanta Mohanty.
Oh, certainly. Is there a library or SDK available for others to learn entropy computing paradigm and develop research and applications on it, like Qiskit?
Thank you. That's a really good question. So we are a hardware company. So our system is supposed to be for on-prem. So we have a software package for on-prem. For cloud access, we have Catalyst that you can find some resource on our website if you go to resource library. So we provide some of the tutorial there that you can build your application from your browser. And it's gonna continue to develop. We're gonna continue to upload more tutorial, and we're happy if you have any specific application in mind that are not in the tutorial. We're happy to work with you on that. Thank you.
Number 2, the anonymous one is good next.
What wave function is used in creating this?
So this references slide 18. If we go back there, so the wave function of the photons going through.
Yeah. So this slide, let me go back to the system so it's easier to explain here. So you can see that wave function here is basically when you have your Hamiltonian encode your linear loss as the amplitude of the wave function of the and we use like a digital to analog converter to create an RF signal modulate over optical modulator. And that is a single photon wave function, but basically it's a weak coherent state. So it's probabilistically. That's why we have the mean photon number controller, where we try to maintain that the mean photon would be less than 1%, which equivalent to 99.9% of the time that your wave function is represented by a single photon. Does that answer your question?
So. Oh, and then this might be a final general question from Pedro Jose Maria Rosa.
Oh, sure. So could you explain in more detail how entropy quantum computing works and what sets it apart from other quantum paradigms? And how does the efficiency and accuracy of your method compare to other current quantum and classical approaches for solving optimization problems?
So I refer you, Pedro, to the paper that we just posted on archive.
Okay.
But in general, we can say briefly that this is fundamentally this approach is different. The main idea, as I was trying to explain, it was to embed basically a given Hamiltonian into a dissipative operator, and then basically you use that mechanism to search for the ground state, and in principle a high dimensional search space. How it compares, the principles are completely different from a quantum gate-based model or a quantum annealer. I cannot enter and explain each one of those, but the principles are different in each one of those. And the second part of your question, we are benchmarking. We are still basically we are still benchmarking, but clearly we see several advantages already. The main thing is that for a lot of quantum annealers, but whatever basically there's available, you can only do QUBO and Ising at this point. Anything else you have to do, there's a lot of cost basically to formulate it that way. That it starts, let's say, even from basically embedding of the problem to a sparse matrix in the form that they accept that, and then going to the part that even there are a lot of problems that in principle are not binary, or they have basically these non-quadratic terms, which we can readily basically test them with our system, and we see basically the advantage over power, over speed, or and as well as the accuracy as well. And similar basically with the classical approaches, we are basically benchmarking that, and we already see basically very exciting results, and continue to explore that. Yeah. But if there's a particular approach that you have in mind, I'm happy to discuss further.
All right, that kind of concludes our questions for today, and in our presentation. I'd like to thank our presenters, the panel, and of course our behind the scenes assistants, Drew, and Russell, and Nicole, and everyone else that helped on the presentation. So we certainly appreciate everyone doing this, and we hope to do more of these webinars in the near future. Thanks so much.
Thank you.